I will talk about my work, my team work on planning with a learned word model, or planning in imagination, as I like to call it. And we'll start with a brief introduction to reinforcement learning framework. But in contrast to the previous speaker, I will focus on the issue of planning and learning. Then I will introduce a problem that we try to solve. I will talk about our solution experiments, and I will show you some qualitative results. And then at the end, we'll compare this solution to model-free and model-based state-of-the-art baselines. There should be also some time for a Q&A session. So yeah, reinforcement learning is learning what to do, how to map situations to actions in order to maximize some notion of cumulative rewards. So we have this agent and the environment, and the agent, in order to learn, takes some action in the environment, and the environment fed back some state and reward signal. And the agent wants to maximize this reward signal. It works as a reinforcing signal, and it conditions its actions on the state signal. The behavior of the agent is represented in something called a policy. You can think of it as some treasure map. So you have this map that tells you that you have a state, and in each state what actions to take. And in really short, the RL algorithms are all about finding this policy. So there are two fundamental approaches to learning this policy. There is something called model-free reinforcement learning, in which the agent samples episodes of real experience by interacting with the environment here, and it learns from it, and it's called learning. And there is this model-based reinforcement learning, where the agent samples episodes of simulated experience using its word model, and then learns the policy from this experience. And this is called planning. And as you can notice, you may notice the symmetry between learning and planning. You may use the algorithm for learning and planning just by substituting the simulated experience in place of the real experience. And to be clear, what is the difference between the environment and the word model? The environment is some black box, so you can just interact with it. You just do some actions and get back some states and rewards. And in the word model case, you can just ask the model, in this particular state, if I take this particular action, what will be the next state and the reward? Okay, the problem statement. So, as I already said, one of the most important branching points in RL is if the agents have access to or learns the model. And the main upside of having the model or learning the model is that the agent can plan ahead, and he can just see what would happen for some range of possible choices, and then explicitly choose between his options. So he just distills this knowledge, this planning knowledge, into learned policy. And when it works, it results in a really sample efficient algorithm, and more sample efficient than the other methods, model-free methods that don't use the model. So yeah, for example, the model-free methods in benchmark of Atari, Rainbow, the method called Rainbow, needs about 100 million time steps or interactions with the environment to learn something sensible. Like this 100 million interactions is about 1 month of interacting with the environment at 60 frames per second. And in contrast, those model-free methods need about 100,000 interactions with the environment. So this is like 3 order of magnitudes less data. And I don't need to remind all the ML practitioners that data is our gold, and RL is not different in this aspect. So one of the main constraints that keep the RL from being applied to some real-world applications is this sample efficiency. The main downside of using model-based reinforcement learning is that the model of the environment isn't, the ground truth model of the environment isn't always available. So we need to learn it. And we need to learn it from the experience, which creates several challenges. The main challenge is the bias in the model, or the small errors that accumulate over time. Here you can see Here on the diagram, you can see some starting state from the environment. This is ground truth state from the environment. And then there was some sequence of actions that was executed in the learned model. And here you can see that the learned model, which imagined what will happen next, changes some types of some blocks, can split the agent into two. Then it models the agent right, but still some blocks change their type. Then maybe the agent disappears at all. And and those errors can be exploited by the agent, resulting in the agent that plays well in his imagination, in his head, but then does really poorly or super terribly in the real environment. And and model learning is fundamentally hard. So even even intense efforts can fail to pay off. Yeah, and let's move to the goal of our work. We just wanted to improve data efficiency of RL algorithms without loss in performance, and compared to model-free state-of-the-art baselines. And we choose to go this model-based approach, and we used. We're focused on 3 benchmarks. Those are the Atari games, boxing, which is dense. If you know the RL, this is like dense reward and arcade game. Then you have this game Freeway that we won't talk about because we have not that much time. And there is this game Sokoban. You don't need to know details of those games. Those are just some benchmarks that we try to optimize. Okay, solutions and experiments. So while model-free methods forego this potential gain in sample efficiency, those are often easier to implement and fine-tune. So this is the reason why the model-free RL is more mature. Like more researchers focus on this. And nevertheless, there are some successful stories in model-based RL too, and we based our work on it. Here you can see that we look at 3 example solutions, and we look at them at 2 perspectives, the word model and the planning strategy. And the first one is simple. You may heard it already because my friend Piotr presented it, not for Atari games, but for learning schedules for learning the transformer. And this it is characterized by the fact that the word model is in observation level. So it means that it takes, for example, raw pixels as an input, and it outputs an action, and outputs raw pixels of observation. And this model is used in this work to just generate more experience for the model-free algorithm to learn how to behave. Then we have this word models work. It is different in the fact that they use abstract level models. So there is this module called vision, you will see it later, that just embeds the raw pixels into some feature space, for example, agents' positions, etc. This is learned feature space. And then they trained some model-free, or in this case, it was like some evolutionary strategy controller in this abstract level model. Abstract level space. And there is the last one, the approach that we took. This is called PlaNet, similar approach to the one we took. This is called PlaNet, and this is also abstract level model, but the model isn't used to generate data and learn model-free policy from it. It is used to search. So you can imagine that you build some tree of the game and you search for good actions. Okay. So yeah, the first iteration just tried to take the word model, and we called this architecture original word models. And maybe in short, what is this architecture? We have this vision module that, like I said, it takes the observations and outputs some abstract level features. Then we have this memory module that is just some recurrent neural network, some RNN. So it has its own hidden state inside, and the memory takes its own hidden state from the previous steps and the embedded state from the vision, and just tries to predict the future. And in the work, in the original work, there was this module controller that just took this representation from the vision and this representation from the memory to just choose an actions. And the idea was that the vision will summarize the spatial features of the observations, and the memory will summarize the temporal features of the observations, so across time. Of course, we've substituted this controller with something different, what I will talk about you later. Yeah, vision was just some versional autoencoder trained to reconstruct input images. And one important information: this architecture didn't collected data online. It just collected data before training from some random agent. So the random agent just explored the environment, data was saved, and then in supervised fashion, we just trained the model, the vision, and the memory module. And the memory was this RNN that was trained to predict the next output of the vision, the next state in the abstract feature space. It models dynamics with mixture of Gaussians, and it models its deterministic hidden memory with RNN. So yeah, we have this hidden state of the RNN, and then this hidden state is used by some by mixture of Gaussians used to model the next state. So it means that this model is stochastic, right? We just we sample next state from the distribution, and the distribution is created by the RNN. This is really important, and we'll get back to it. And here are some results for the game of Sokoban. So here you can see the ground truth images of vision for vision that was given to vision, encoded and decoded. And you can see that there are still some artifacts, even in vision. Well, it is quite good, but there are still some artifacts. For example, here the block type changed from the box to the wall. And here we can see that the wall changed into another agent. So yeah, there are some artifacts, and the model didn't train like I said. There are those errors, and here you can see that the agent just disappears, or the agent split. So yeah, the memory didn't train well. And what we tried to do with it was, okay, if their vision already have those artifacts, so maybe we'll just bypass the vision and pass the representation that is just 10 by 10 matrix with block type in each cell. And maybe this way we'll have this ideal vision, and maybe memory will do this with it better. But yeah, it didn't. Reasons why there are many, possibly many, but the one thing is that the memory, it is still pretty raw representation. And Sokoban, yeah, I need to mention that Sokoban have really big state space, because every time we start new episode, the board is sampled, generated from randomly. So each time the agent starts living again, he just got the random board and have to deal with this huge state space. And this representation doesn't help because this is still a raw representation. So we thought, okay, maybe we'll try something to learn better representation in the memory. And there is this work from DeepMind called auxiliary tasks. So you just apply some other tasks to this learning to just boost the learning of good representation. And we just tried to train the model jointly with some value function, but it didn't help too. Okay, but then we moved to boxing, and in boxing it worked like ideally. You can see that those reconstructions are pretty much exact. And the memory also worked pretty well. Here you can see that the weight agent smoothly moves his hand back and then pushes the other hand, the right hand. Yeah, and yeah. So we had this good model for the boxing. This was time to plan with it, and we thought that we will want to use the Monte Carlo-based algorithm called AlphaZero. And which we wanted to use it because this is state of the art, and general purpose. But this algorithm, Monte Carlo tree search, yeah, I know. This Monte Carlo tree search algorithm needs in its basic form, it needs the deterministic model. So we just thought, okay, we'll cut the stochastic part, we'll leave the deterministic part, and it broke the model. So yeah, so we needed something that can work with stochastic models, and we moved to the next work, PlaNet. And PlaNet uses this planner that that is called the cross-entropy method, and yeah, this is really simple method that is just initialized with some historical data. So we have some history of states and actions. We initialize our model, then we roll out our model for multiple random plans. We choose the best one that happened, the best according to sum of rewards, and we fit our actions to the best plan. We then, again, in the next iteration, we just sample more plans, fit to the best, and after, I don't know, about 10 iterations, we have pretty good actions distributions, and we just choose the best actions, the best first action. In Sokoman, it still didn't work, but in Boxing, it worked quite well, the model. And here, what you can see, there is some plan that is executed in the environment and in imagination. And so here you can see the exact observations from the environment, and here you can see what the agent just imagines in its head. And this is like really, really good. You can see that the white agent is pretty much exactly reconstructed. And this is like what we wanted to achieve, because this is the agent we control, so we need to exactly know how it will look. But the black agent, because it can take some stochastic actions, the imagined future may differ from the ground truth. And we can see that the white agent hits exactly like in the ground truth, but the black agent behaves differently. Okay, and this is like example play. You can see that the white agent successfully drives the black agent, the opponent, to the fence, and then they beat his ass. Yeah, and at this point, I want to remind you that in this little white head, this agent, at each time steps, imagines possible futures, and then from those imagined possible futures, it distills best next actions. So for me, it's pretty amazing, and I was really happy to see it work, because it meant that I will defend my masters on time. Okay, so yeah, this is just to sum up the successful story. Here you can see rising learning curve, something that we all love. So please clap for the rising learning curve. Okay. Some final results for Boxing. So we compared to simple and to two model-free baselines in this low data regime. We maybe not match the simple performance, but it doesn't matter. More important for us is that in this low data regime of 1,100 interactions with the environment, we managed to beat the opponent, and the model-free methods didn't. So you can see that the sample efficiency was achieved. Yeah, and that's it. Thank you for your attention. Maybe I will take some questions.